So now today we're going to continue talking about decision making under uncertainty. So what we're going to do is we did last time, we looked at this. Decision variables are like random variables, but the agent gets to choose a value for. Okay, so they're like these variables that the agent can do. Okay, and now a possible world, we defined that before, was an assignment of a value to each random variable, but now we're going to assign, as a possible world specifies a value for each decision variable and each random variable. So that's what we're going to do here. So we're going to extend the idea of a possible world. And for each assignment, all values to all decision variables. So there's a probability distribution over the random variables. And the probability of a proposition is undefined unless the agent conditions on the values for all decision variables. So what happens is the probabilities are undefined unless we know what decisions being made. And then we looked at this example. The robot can choose to wear pads to protect itself or not. The robot can choose to go the short way, the long way, and there's a random variable of whether there's an accident. So we have this, the agent gets to choose whether to wear pads or not. The agent gets to choose a long way or a short way. And there's a random variable that says whether an accident or not. And then the utility depends on these. Okay? These square boxes here represent decisions the robot can make, and circles represent random variables. Someone asked before in class, well, there's sort of too many numbers here to specify the utility, and there seems to be too much, seems to be too complicated for complicated decisions to do this. So let's look at a better way to do this. So what we're going to do is first of all look at single decisions. So essentially in a single decision, you're going to make all your decisions before you're going to act. And you're going to choose the agent gets to choose a value for each decision variable. And what we'll do is we'll combine all these decision variables into a variable D. Now the expected utility, and we just looked at expected value last time, of a particular decision is the expected utility. It's the probability of all the worlds times the utility. Well, this is the utility, and omega here is the set of all worlds. So for all W in omega, it's the utility of omega times the probability of omega. That's the expected value. And it's only given a decision variable. So an optimal decision is a decision whose expected value is maximum. So it's such that it's a D max, such that the expected value of U, given that you did D max, is the maximum over all the things that it could do. Because that's all that says. Okay. So what we're going to do is we're going to extend belief networks. And now we're going to extend belief networks to include decision nodes. The agent gets to choose a value for. And the domain of a decision node is a set of all possible actions, and we're going to draw it as a rectangle. The utility nodes, the parents, the variables on which the utility depends, and we're going to draw that as a diamond. So here's the example of going to do here. So the agent gets to choose whether to wear pads. The agent gets to choose which way they go. Then there's a random variable that says whether there's an accident, but the accident only depends on which way they go. The accident does not depend on whether they wear a pad or not, and the utility depends on all three. Okay, so that's what we're going to do a single stage decision network. So a single stage decision network consists of a directed acyclic graph with three sorts of nodes. There are decision nodes, random nodes, and utility node. So random nodes are the same as the nodes in a belief network. So we're extending a belief network. There's a domain for each decision variable and each random variable. So for each random variable has a domain like we did in the belief network. There's also a domain for each decision variable. And there's a unique utility node. And the utility node has no children and no domain. Okay. And the single stage decision network has the factors. There's a utility function as a factor of the parents of the decision of the utility node. And so that's going to say what does the utility node depend on. And then there's a conditional probability for each random variable given its parents, just like there was in a belief network. Okay. And there are no tables associated with decision nodes. All right. And now what we're going to do is to find an optimal decision. So we're going to suppose the random variables are x1 to xn, and the utility depends on just some subset of them. So it doesn't have to depend on all of them, it just depends on some of them. So the expected utility given decision D is, well, we're going to introduce all the variables and then we're going to sum them out. So it's the probability of all the random variables given the decision times utility, whichever these variables depends on. The utility can also depend on decision variables. It's just the expected value. But now when we have this product, what's going to happen is that it's just the product of xi given the parents, but we're also going to throw in an extra factor for the utility. So it's exactly the same algorithm we did before. It's just that now there's an extra factor in there and we're computing expected values. So to find an optimal decision, we create a factor for each conditional probability and for the utility. We sum out all of the random variables. And this creates a factor on, if you think about what's happening here, we've got D plus all of these random variables. We're summing out these. So this creates a factor just on D. And it gives the expected utility for each variable in the domain of D. And we're going to choose a D with a maximum value in the factor. So here's an example of doing that. So here's the one we had before, right? There's an accident, depends on which way, and there's utility. And there are two factors in here. One of which is the probability of accident given which way. And here it says that the probability of an accident go you the long way is 0.1 and the probability of an accident given you go the short way is 0.2. This is the probability factor. And there's another factor for the utility. So this is the utility we did last time. So the utility here, the value depends on which way we go, the accident and where we wear pads. Okay, so we're sort of going to miss up the fact that this value is a probability and this value is a utility, because all we're going to do is multiply them all out and then marginalize them all. Okay, we're just going to multiply all of them and then sum out all the variables. Well, it's only one random variable here, so we're going to multiply these two factors together and we're going to sum out accident, just like we did before. And we end up there with this thing. So if you go the long way and there's true, there's a value, the long's false. So for each combination of these is a value. And we want to select the maximum one. So the optimal problem is to go the short way when wear pads and it has a value of 83. Each of the other combinations of this are worse off. So next time we're going to look at sequential decisions.